Okay, good evening, everybody. I think we will start the evening session. Welcome again to another one of our worldwide WiSH webinars. Again, thank you very much to all of you for supporting this initiative from WiSH. A subtle change which you're going to notice over the coming weeks is that our name is changed to WiSH with a small I. Wit, Sport and Health is our official name. But apart from that, nothing will change in terms of the service delivery. And we hope to continue interacting with you with this academic program that we've been offering over the last couple of months. And I think we're in for another very interesting session this evening. I think importantly to thank our sponsors again for supporting this, the Lita and Asino company, who've supported this webinar series. And very nice to have a number of our rugby colleagues with us this evening from South African rugby and from around the world for this very relevant talk. Also to our South African Sports Medicine Association colleagues, welcome once again. And I see that our Dean is on the webinar as well. So to Professor Martin Bella, who's been a great supporter of the WiSH initiative, welcome this evening. I'm going to wrap up there, ask you to please put your questions on the Q&A facility on Zoom, and we'll monitor those and get to as many of them as possible at the end of the talk. But I'm going to hand over to my sport and exercise medicine physician colleague, Dr. Jerome Mampane, the South African Rugby Springbok doctor, who is here to represent the rugby interest group of WiSH, and will introduce our guest speaker for this evening and help marshal the questions and answers at the end. So Jerome, over to you.
Perfect. Thanks very much, John. And thanks to sponsors as well. Thank you everyone for joining us. It gives me great pleasure to introduce Dr. Dario Cazzola, Assistant Professor and Senior Lecturer in Biomechanics at the University of Bath, with a PhD in Human Physiology, focused on the biomechanics of human locomotion. So tonight he'll present his work on spinal loading in rugby activities and rugby tackle mechanics. Dario, welcome.
Thank you very much, Jerome. And your pronunciation of my surname is perfect, so you must have some Italian origin or heritage, of course.
Fantastic.
Cool. All right. So thank you for the introduction and for the invitation for giving this kind of seminar. And yeah, so in the past, I've been working on human locomotion, and since I moved to Bath, I started to do more rugby stuff. And today is what I'm presenting. And really what I would like to do today is to give you a flavor of what are the different steps that you want to do when you want to understand how to minimize injuries in rugby, and more specifically cervical spine injuries in rugby. And I'm going to go through the methods, so the pros and cons of different methods, and what I believe is going to be the future as well. Feel free, to ask me all the questions. I understand at the end of it. Be kind with me. But I will also present a kind of a quite, specific methods related to both experimental methods and computer simulation methods. But I'm not going to talk about the nitty-gritty of it. And if you've got a question, please do ask at the end. And before starting as well, I would like to thank all my collaborators. This is a group work, really, what I'm presenting here. It's not just what I've done. And most of all, I would like to thank our kind of sponsors and funders. The RFU Injury Play Foundation has been funding us for the last 6 years, and the EPSSC, the Research Council in the UK, the Camera Project. Right, so let's dive into the presentation. So now I introduce you the two main characters of my presentations, the two rugby activities we're going to talk about. And as you know, on the left-hand side of the screen, you can see different type of tackles. And on the right-hand side, you can see some scrums there. The main thing that I would like to highlight is that when I see these players doing this kind of activities, I find this fascinating. It's a mixture of like technical ability, power, physical power, and you need to be also, from a psychological perspective, very ready for it. And this kind of combination of factors makes these kind of activities to me fantastic. And the only problem from an injury prevention perspective is that, unfortunately, if we look at the percentage of catastrophic injuries related to this kind of activities, so both scrummaging and tackling, unfortunately, 40% of the catastrophic injuries in rugby are related to those activities. And it means there are quite risky activities. And what you want to do from an injury prevention perspective, biomechanical perspective, is to minimize them. And mainly because, you know better than me, this kind of catastrophic injuries may lead to paraplegia, tetraplegia, quadriplegia, and that kind of those kind of injuries can bear like very high costs, not related only to medical costs, but also to societal costs as well. Right, so unfortunately we know that that's the problem. So we know that we want to minimize them. How do we go for it? How do we do that? And in injury prevention, there are many different injury prevention models. And this one is, I think, the oldest one from Van Mechelen in the 1992. And it's the simplest one, but I think to me is the clearest one as well. There are also other very good models from Karen Finch and from Roald Barr and Crossog as well. But the main thing is that when you want to understand how to minimize injuries, you want to first of all establish what the extent of injury. So you want to understand what's the magnitude of those injuries, so the severity, how much, how frequent they are, and therefore how big is the problem. When you know how big is the problem, then the next step is indeed to understand what are the causes of those injuries. This is very important to me, and then that's very close to my research as well, because understanding the causes of injuries means that you understand also how to prevent them. And that's the work. If you're a biomechanist, this is the kind of step in which you are working on. Once you know the causes, this kind of causes should, this kind of information, this kind of knowledge should be used to inform ideas for prevention. And when you come up with your intervention or your injury prevention strategy, then you assess whether that works or not, and hopefully it does. So I'm going to focus on step number 2 again, because it's more like biomechanics related. But if you look in the literature, there is a lot of work that's been done in the last decades, and the only problem with it I see is that most of the studies are observational studies, and there is a big debate in the literature between Custer and Dennison, but again it's more based on qualitative type of research. There is a lot of video analysis, which I don't have anything against it, of course, and I think is very good to have. But with video analysis, you can get not that close to the injury itself, because you cannot know what's happening. When for example, the head is very close to the torso of the head of the tackler is very close to the torso of the ball carrier, for example. So it's good, but maybe it's not good enough. There are lots of personal reports. There are more kind of detailed kinematics and kinetics analysis, so analysis on the motion, so kinematics and kinetics on the forces that happen during a tackle mainly, but those one are usually are kind of performed in the lab. And usually, in the last probably couple of years, the focus is mainly on concussion rather than cervical spine injuries. So to me, what I want to highlight today is that really we don't know yet what are the injury mechanisms related to cervical spine injury in rugby. And this kind of debate I was talking about was mainly between hyperflexion as an injury or buckling as an injury. I'm going to talk about those mechanisms later on, but just to give you a flavor of it, hyperflexion is, of course, when you are trying to bring your chin very close to the torso, and that kind of injury is mainly related to high flexion, very high flexion of the great flexion of all the vertebrae, cervical spine vertebrae. Buckling is more like a different type of mechanism, which is mainly based, mainly kind of related to a very high compressive force application. So as you can see, the force here is applied. Maybe I can do this as well. The force here is applied on top of the head, is a compressive force and causes different type of motion of the vertebra. But the big problem again is that really what we are missing from all this kind of study is the clear link between what's the external load applied and the internal load experienced at the intervertebral level. If we don't understand this link, we cannot understand what are the injury mechanisms, and we cannot understand how to prevent those injuries. Right, so that's the kind of theory of it. But you know, you start this journey and you say, all right, but how on earth am I going to do it? So I think the first step for me was to come up with key variables that I believe are the most important ones. And the key variables for me are related to, of course, the load applied to the system. So when you're thinking about preventing, you know, how an injury happened, the two main kind of variables to me are related to the load. That could be external load or internal load. So internal load, we're talking about the muscle forces generated or the passive forces generated by other structure. And the second one is the motion. So I know the force, but I would like also to know what's the motion of the different anatomical segments of the body or the different vertebrae. And this kind of two variables are key then to understand how we exceed the limits of our system. And therefore, we're going to understand, hopefully, what's the link between the external and internal load. So these are the key variables: external load, internal load, passive response, body segment motion. But the next question is like, okay, I know that I want to measure those ones, but how am I going to do it? So what kind of methods I can use to do that? Well, I really like to do, not to master specific things, but to not master many of those. So I'm not an expert in anything, but I do lots of things. And I truly believe that an integrated approach is the answer for this. So in my research and in general in kind of injury biomechanics, injury prevention research, there are different methods used to answer a specific question. And in this case, me from a biomechanical perspective, in vivo, in vitro, and in silico are the methods that we want to look at. So what are the differences between the three methods? Well, in vivo comes from, all of them come from Latin. So being Italian, I can kind of know it. You know, in vivo means that you are working with a living organism. And a rugby player is a living organism indeed. And what you want to do, you want to test things when this kind of organism is a whole, and you are not essentially segmenting in different parts, and even though there are many factors that can play a role being an in vivo you know, study, for example, the psychology of a player can play a role in that, but you want to have that as an input to other methods, because it's the most kind of true kind of analysis that you can do. In vitro means the other type of method is in vitro, means that you are doing things in a glass, and from Latin, and it means that essentially you are not dealing with any in a whole living organism anymore, but you are picking a part of it, and you are trying to recreate similar condition to in vivo, even though it's very difficult to do. And as we did here, so I'm going to tell you what this is, because otherwise you're not going to understand it. These are 3 pig spine. And we gave a whack to the pig spines and to replicate some injuries. And here you can see there are different vertebrae here, and there's some tissue, soft tissue around. So we are trying to replicate some injuries in some conditions which are not, you know, ideal, but at least we can do something that we cannot do in vivo. The other solution is to do anthropometric, anthropometric testing devices here, so dummy heads. These ones, in vivo, in vitro, are mainly experimental methods. What I really like to do in my research is to integrate those experimental methods with more computational methods. So in silico methods, in silico means in a computer. So essentially, when you run in silico analysis or simulation, what you do, you run use a computer to run some algorithms and using some mathematical models. That could be musculoskeletal models here or finite element models here. Right. So how we know that these kind of, we're going to use different methods, but how do we link them up in a proper way? So the first step to me is to always start from something that is real. And that's the reason why, for example, video analysis can be very good and is a very good starting point, because I want to understand everything about what's happening in the real world. And when I do so, I try to replicate that in the lab. I do understand that video doesn't look like a real tackle, and I apologize because I've got better videos I'm going to show you later. But the idea is that you try to recreate in a controlled environment what's happening in the real world using in vivo testing, so rugby players in that case. After you do that, what you can do is you can add on top of it some analysis using computer models or mathematical models. So you recreate the movement in a computer, and in this case, you can, the big step is that you can essentially try to understand what are the internal forces applied onto the system. So you can run some inverse kinematics, inverse dynamics analysis. Don't worry if you don't know what they are, I can explain it if you want. But mainly you can calculate some joint reaction forces and estimate what are the muscle forces generated during a tackle. And that's very important because that will, first of all, for the first time, give you a bit of a link between what's the external load applied, so these kind of green arrows here, and the internal load experienced at the vertebral level. This is a pathway which is very important, and it's been very much used in biomechanics. However, if you do so, really what you're doing, you're studying a non-injurious event. You're analyzing a non-injurious event because, of course, you can ask many things to rugby players, but you cannot get them injuries in the lab. So what you want to do, you cannot replicate injuries in this way. But there are other ways to do so. So you might have already understood that if you use in vitro testing, even though it is less kind of realistic, if you want, as a test, you can try to replicate some injuries. In this case, we use an anthropometric testing device to replicate head first impact during a tackle. And also when you measure this kind of motion and forces using kind of, for example, a dummy head here, what you could do, you just still can use this kind of information to run some in silico analysis. And this, in the same way, you can run inverse kinematics, inverse dynamics. You can calculate the joint reaction forces at the vertebral level, which in this case are mainly passive because there are not many anthropometric testing devices that are actively activating muscles. That maybe in the future will be a great thing to have. But the main thing here, the main message for this slide is that in this case, only in this case, you can start really understanding something about injurious event, whilst using in vivo testing is not possible. Right, so now I want to give you another kind of way to mix this kind of methods up and providing potentially even better understanding of what's happening out there. So let's start from the same kind of starting point, and let's say that we do the same thing that we said before. So we do in vivo testing, we do some in silico analysis. And if we do that, as I said before, we get very good information about the non-injurious event. So that means that you got a very, quite real kinematics. You get information about the technique. That might be also your optimal technique. You get information about muscle activation in vivo. So you can use EMG, so electromyography, to understand how the neck muscle and the trunk muscle are activated. And that's very, very important information. At the same time, you do what we said before, and you run some injurious event using in vitro testing. You get here more information about what's the external load during injurious event, what's the tissue strain during injurious event. And the last step, which is to me the most exciting one, is that you can merge this information. You can use different bits of information that has been collected in different ways to run some simulation in this case. So just to clarify, here I was talking about in silico analysis. And here I'm talking about, I could have called it in silico simulation, but there is a difference between analysis and simulation we're not talking about later on. So FD means forward dynamics. Essentially, what I'm doing, I'm using a mathematical model or a musculoskeletal model. I'm applying a force to it. I'm applying a specific, for example, muscle activation to it. And then really here, I'm replicating an injury that might have happened in the real world. Using information that is coming from in vivo and in vitro. So it's a very good combination, and then creating new kinematics, a new injury, using this forward dynamics simulation. This is just to clarify, I think it's quite important, the difference between analysis and simulation. So in biomechanics, analysis is mainly used when we run inverse simulation. So inverse means that you start from the kinematics and you understand what are the forces that are generating that kinematics. And usually an analysis is driven by in vivo, in vitro data. So it means that you've been in the lab, you collected something, and then you apply a model on top of it to calculate some parameters or some variables, mainly internal variables. A simulation is something different. Simulation is called forward, usually simulation. So you start from the forces and you get the kinematics. And the main thing to remember is that it could be initially driven by some in vivo, in vitro data. So you need to tell the simulation, I'm going to start with a head this way, with a muscle force at that level, with a force apply of that magnitude. But then after that, what you do, you generate new motions using a mathematical calculations or integration. And then after you got, when you do so, essentially, you will see that the head will move due to the force applied to it. And then once you got that, you can go back to the analysis if you wanted. That's an example of what we have been doing like in vivo testing. So that's we try to replicate different tackling events in the lab. We study different type of tackle angle using a punching bag of 40 kilo. And which I know it doesn't sound like a big lad, but believe me, if you accelerate a 40 kilo punch bag against you and you're not expecting it, most of all, that kind of punching bag is not avoiding you, is a big hit. And we use also some pressure sensor on top of the punch bag so that we could estimate some forces. We use some force plates to measure the force generated in the ground reaction forces, and we use a motion capture system to get 3D motion of the players during different type of tackles. So that was a 45 degrees, I believe. There's a frontal kind of tackle. We did also 90 degrees as well. And we also measure muscle activation, as you can see on the back of the player here. And you mainly kind of measured the sternocleidomastoid traps and erectospinae and latissimus dorsis, I think. And this is an example of how many people you need to do that and how long it takes. I think it's 2 hours kind of compressed in a few seconds. And there was only one operator, I promise. And this is, the whole thing we kind of use a video camera, like a GoPro, I think, to collect these videos. Yeah. Right. So that's an example of what you can do in vivo. We did similar things with the Scrum. I can show you some videos as well if you're interested as well. But the thing is that I'll try to give you some take-home messages about that. So why is good to do in vivo analysis in rugby? It's good because you can get a very good understanding of the tackle technique. And it's very difficult to get that tackling technique from video analysis. And then mainly this kind of kinematics analysis gives you information about the head position, head angles, the trunk angle. This is a very key information to then run forward dynamic simulation, as we'll see in the future. Also, I mean, it's very interesting. I think Tanabe et al. In 2018, they also managed to do a very similar study doing actually stage tackles using 2 players, so a tackler and a ball carrier, also simulating a BADI technique in vivo. We've been using those data as well to run some simulation. It's amazing what you can do in Japan, apparently. But that's another good example of what you can do to understand how things can go bad. So that's a hybrid kind of test between in vivo and in vitro, as I said before. The other good things about doing in vivo stuff is that you do understand how people do prepare, how players do prepare before an impact. As you would expect, if you are trying to tackle someone, you're going to prepare your muscle, your body, and there is we saw there was a very high muscle pre-activation. Probably was higher during scrummaging than tackling, but that's very important. So you are, to some extent, stiffening up your body before the impact. What is less good is the estimation of the forces. Well, using pressure sensors, we estimated some forces during tackling, which were changing, as you can see here, across the different tackle angles. So the tackle force, of course, was decreasing, from 0 to 90 degrees tackle. There was also a difference in terms of what kind of shoulder they used. So more like dominant shoulder, non-dominant shoulder. And we also saw that there was a more passive behavior using the non-dominant shoulder than the dominant one. We can talk about that if you've got questions later on. But the bad thing about it is that, okay, we can measure it, but we are not very happy about the reliability of that measure. We are happy with the shape, the curve shape, but not the reliability. So this kind of 6 kilonewtons here might be true, but I believe it's a bit high. That's my opinion. Right, so let's move from in vivo to in vitro. I'll give you some examples here. Again, to do in vitro stuff, you can mainly go 2 ways. The first one is to buy an anthropometric testing device, or dummy head here. Very nice because you can make your colleagues run after a bag, which is very funny. But these ones are kind of mainly used in automotive type of research. They have got a load cell at the between C0, C1, and the skull, which is very accurate. But again, maybe the actual passive response of those kind of anthropometric testing devices is not as good as, for example, another kind of type of test you can do, which is based on the use of animal specimens. And in this case, again, I'm showing you 3 different pig spines that were like loaded with a compressive load, which was the same that we measured during actually scrums. So that was replicating a scrum injury. And as you can see, unfortunately, there was actually a burst fracture here. As you can see, there is some bone marrow flying away. Sorry if you don't like it. I guess it's not nice to see. But again, in this case, you can also use video cameras and try to measure the tissue strains at the vertebral level as well. So what you do, you can use a DIC, which is a digital image coloration in this case, and you can get essentially the deformation of different bits of the specimen. And the forces that we measure with forces measure at the cranial and caudal, so at the top of the bottom of the specimen. So why is good? So it's good to use in vitro because if you go in vitro, for example, you can also use not MRI, but CT scans. You can CT scan this kind of specimens, and you can create a finite element model, and then you can replicate the same kind of impact, the same kind of deformation if you got a very good model. So that's a good thing about using in vitro stuff. But mainly, just to give you another idea of what you can do here is you can replicate really cervical spine injuries. So in this case, we're replicating injuries, something that we were not doing before, even with the anthropometric testing devices. The other important, so that's an example of what you can do with a DIC, so digital image correlation. You can see there are different values of strain. The red ones means a very high kind of strain, and blue one's very low strain, you really can quantify the structural damage. So as you can see here, it's a different level of information. It's not about what's happening externally, it's about what's happening kind of internally. We also did some angled kind of tests. We still need to analyze them, but you know, you can really try to replicate different type of injuries in this way. The other good things about in vitro stuff is that really, as you may know already, unfortunately, the most common injury in cervical spine injury in rugby is the anterior bilateral facet dislocation in the lower cervical spine. So usually between C4, C5, or C5, C6. So C4, C5, yeah, C4, C5, C5, C6, C6, C7. And the good thing about our kind of tests, in vitro tests, is that we did manage to replicate those injuries. So we had some bilateral facet dislocation at the same level, even though it was a pig spine. We had the same type of injury, which it doesn't tell you what exactly is the link, because we couldn't really measure the individual vertebral motion. We just measured the external strain there, as you saw before. But to us was a very very important kind of step, because we thought that we were very close to replicate injuries that we saw unfortunately in a rugby scenario. So we were very happy about it, we also. But even though we were very happy about it, we also tried to use some anthropometric testing device just to have more information about the variability of the load that could be applied to the head. And what we did, we tried to replicate different type of scenario, like related to head first injury in tackling, so head first impact in tackling. And we did put the dummy head at different angles, like with a head up, neutral kind of position, a head down. And we also accelerated the punching bag at two different speeds, a high speed and a low speed. And as you can see here, these are the traces that we generated in terms of forces. And what we saw is that with a head down, the forces at both kind of high speed and low speed were higher than a neutral and head up position. And you know, that was good for us, because we kind of replicated at least the dynamics of an injurious event. We had a very good force measurement, very reliable force measurement, and this kind of, you know, curves are so neat and clear, and you know that you can easily use in a computer simulation. It's difficult to input in a computer simulation a very rough, you know, noisy kind of curve. So it's very good to have this kind of information if you want to run some computer simulation after that. The problems related to using ATDs are mainly the biofidelity. So is that really what's happening during a tackle? I don't believe so. The range of motion of the head is different. We're talking about actually a passive response. There are no muscles. There's a bit of stiffness within the neck, but it's not really comparable to what's happening during a full muscle activation, or more like physiological muscle activation. And the stiffness again is also can be changed. So we set it out to a specific value, but that value might not be you know, good enough for this kind of analysis. So we believe that the force, the curve of the force, the magnitude is potentially good enough to use to be used in a computer simulation, but we know that it's not the best solution, and we need to work on it to improve it. What we also did was something that was a bit of a hybrid solution between in vivo and in vitro. So as you can see here, there are there's a 3-man scrum, and the hooker loses that entire head, and there is a dummy head here. So essentially we use a machine, a scrum machine here with instrumented beams as well, and those kind of forces there. but most importantly, what we did, we also measure how the hook head was activating the muscles. And we did see in that case, there was a very high reactivation just before the impact. And that's essentially what you expect. And that's very important for us because that will be an input to our computer simulation. And we do know that players do activate quite a lot the muscles before the impact. Again, the other problem using ATD is the biofidelity again. So that kind of the forces that we measured might not be as reliable as the one that you measure with a force transducer between two players, which is impossible to do. But that's the kind of the biofidelity is still an issue. Last but not least, you're talking about the key methods in terms of in silico methods. And really, if you want to do this kind of research, what you want to look up are three main things. You want to be kind of aware of what a musculoskeletal model is, and you want to know what are the pros and cons of using musculoskeletal modeling. For example, a musculoskeletal model is a multi-body model which is based on a rigid body assumption. So those kind of models here are built up by different anatomical segments, but these anatomical segments cannot be compressed. There is no deformation of those segments. They are rigid. And that when you're talking about injuries, you need to be, sorry, my son is around, I think. And you need to be sure that you stop, for example, your simulation before a very high deformation is happening, or you think is happening. With musculoskeletal modeling, there are also some muscle models within those. So you can solve what we call redundancy problems. So essentially, you try to estimate what are the muscle activation, muscle forces generated during that movement. And I can talk about that more about that in the future, if later on if you need. And the other kind of a second kind of type of method you want to be aware of is content modeling. So this to me is the future, and we are started doing some work on it. Essentially, you want to use other type of models that essentially are replicating the forces that try to generate or estimate the forces when you got penetration between two objects. And then, for example, in rugby, in my case, what I'm thinking about, you can replicate the forces that are generated when the tackler head is going against the ball carrier's torso, for example. This is very good. They are based on different type of methodologies like Hertzian content models or elastic foundation content models. But there are different solutions that could be explored to do so. And then finite element analysis. So to be honest, finite element analysis is are the best ones, and finite element models are very detailed. So the main difference here is that you got very little elements within the same vertebra, and you can get information about how the load and the stresses and strain are changing across the vertebra. And you can create deformation using these kind of models. But they're very difficult to use. It's very difficult to set up a forward dynamic simulation, a finite element analysis. They are mainly used during quasi-static events. It's very difficult to use them during impacts. So what I see is like, musculoskeletal modeling and content modeling are two steps to go towards the finite element analysis. And in fact, finite element analysis can be used, MSK modeling can be used to provide some initial condition to finite element analysis as well. So if you want to go for like in silico analysis, the other kind of question you need to ask yourself is, what kind of model do I need? So do I need to go for a whole body model? Do I need just to focus on a specific parts of the body? And the model complexity, so for example, the degrees of freedom of the model, is a very important thing to get right. And as I would say in the future, at the end of my talk, I think less is more. So if you don't know how to go for it, you just go simple. And but you need to have some rationale to do so. So, for example, you can have a very generic, not very specific model for the lower limbs and pelvis and torso, but very detailed model for the cervical spine. As you can see here, there's a core model here with different ligaments. But the important bit is that you can really understand what you need to really capture within your model is the passive response of your system. So are they using this kind of ligaments, or using a more kind of a simpler kind of approach, using, for example, lumped parameters or bushing parameters? You need to be able to, your cervical spine should be moving passively as a cadaver will do, for example. That's very important to replicate, really, to be able to replicate injuries, realistic kind of injuries as well. And also, when you create your model, you want to understand if you need a torque-driven model, so having just like a ideal kind of rotational force generators, or you want to use muscles, you get a muscle-driven model like the ones that you see here. And you want to understand how important is to get the muscle paths right. When I say muscle paths, it means that if you think about a rugby players or like a normal healthy individual, you will see that the muscle volume and the muscle and they look different, and they look different mainly for the muscle volume. And the muscle volume is very important, and the shape of the muscle is very important, because the shape of the muscle will also give information about what's the moment arm generated by between those muscle, the line of action of those muscle and a specific joint. I'm going to show you later on. But that's important, because if you need those kind of inertial muscle paths, you need to get some imaging, for example. Yeah, so this is something I already kind of can touch upon before. When we, in this case, when we were talking about passive response, in our case, what I believe is important is to really be able to replicate what's happening at intervertebral joint level, and how the disc, the intervertebral disc and the ligaments are resisting some motions. And when you create a model, the first question you need to ask yourself is my model good enough? Usually the answer is no. And then you ask yourself, is my model good enough for input events? And the answer is no. And so you need to work hard to make it reliable and to make a good model in this case. And this is something that we tried to do as well. So that's again another kind of pig spine that we used. And in this case, what we wanted to do, we essentially we wanted to not only get the overall the strain on top of this kind of vertebra, we wanted to get the individual vertebral motion. And our approach was to say, really, I don't want to know exactly what different ligaments are doing. I want to know, I want to maybe try to model this kind of passive behavior just using a very simple spring dampened model here. And we put this kind of spring dampened models in between different vertebrae. And then we run some optimization, trying to see whether by changing the parameters of this kind of spring and mass, so the stiffness and the dampening parameters of these models, we can replicate the same movement that this kind of spine has got during an impact. That's just a video to show you what we've been doing. So we've been using a motion capture system at 4 kilohertz, and these are the clusters that we used during the data collection. And here, what's important you can see is the model, and in pink you see the actual model markers, the simulated markers, and in blue the experimental one. And as you can see, they are on top of each other, which means that actually my model is moving as the pig spine in the real world. So I believe, so in this case, I'm very happy because my passive parameter and my passive response of the spine is good enough. So I'm validating my model, which is a very important step to do. So really, what I want to highlight is that that was a very important step that we did. It was a bit boring, it's not as exciting as doing like in vivo tackling, but is a key kind of step, because now we got very good information about the viscoelastic parameters that characterize the response of the cervical spine. Of course, there are some cons because, still using an animal specimen, and the material properties and intervertebral angles between vertebrae here, there is a bit of a curvature, a bit different. We have been doing that mainly on axial impacts. We've got some data with like more angled ones with more shear forces. But again, we can, I think that was a very important step, and we did, I think, quite well doing that. Right, so before I was talking about muscle path, the importance of, getting some medical images. And after a while, we understood that we did need them. And what we did, we asked rugby players to get into a MRI scan, and we get the scan. That's a transverse view. There will be a sagittal view later on as well. We use some fish oil markers to register the position of the body with our kind of computational model. And as you can see already here, the muscle volume is massive. That was a prop, and academy level prop. And what Pablo Silvestre has been doing, so the PhD student has been working on this project, has been segmenting this kind of images, has been trying to find, using MATLAB, the centroid line of those muscles, which is very important indeed, because as you can see here, this kind of line is very important because will dictate what's the perpendicular distance between this line and the joint here. And if this distance is very high, it means that you don't need a very high force to generate a motion. But if this distance is very, it's not, it's very low, then it means that you need very high forces to generate a motion here. So the moment arm is very important, and this kind of way of like doing things will allows you to generate, to calculate very good moment arms as well. That's been done for different muscles, and also what we did, we created some, as you can see here, some different geometries. So we use a sphere, we use a torus, we use a cylinder as well, and we did use that because also we wanted to wrap around the muscles in order to generate realistic path. Because if you got just a line, which is just a straight line from a point to a vertebra, that line is not really replicating what's happening during, in the real world when you are flexing and extending your neck. So if you use this kind of wrapping surfaces, the kind of muscle line in the model can wrap around those one and create much more realistic models here. As I was saying, this is the OpenSea model, and as you can see here, the torus is used to wrap around the trap, and the sphere is used to wrap around the sternocleidomastoid, and the cylinder here is used to wrap around some muscle like the semispinalis capitis. And also we use MRIs to get some information about the maximum isometric force of the muscles. All right, so at this point we got a very good information about the viscoelastic parameters. So what's happening to the model when is kind of loaded in a passive mode. We know we got our model very much like a subject-specific model with information about how the muscles are running across the neck and things like that. The next step is to be able to estimate plausible or physiological muscle activation. And the muscle force is one of the most important forces that has got important role during an injury. And what you want to have if you want to study an injury is information about the external load, gravity, inertial load, so it's the acceleration, for example, of the skull. But mainly you want to know what are the muscle forces applied between the skull and the trunk, so across the cervical spine. A good way to understand how the muscle activated is to use some fine wire and essentially get some needles and get to the muscle belly. But of course, that's was impossible to do during rugby activities. So what we did was a slightly different approach. So we used like normal surface EMGs during scrummaging and tackling. And what we did, we mainly put this kind of EMGs on the sternocleidomastoid and the trap. And we tried to use the information to group some muscles. So we kind of our hypothesis was that superficial and deep muscle were activating quite similarly, even though it might not be true, and we were grouping them in that way. This is something about the redundancy problem. Maybe I'm going to skip it or just give you an idea of why it's important to do what we're doing. So usually in biomechanics, what you want to do is to, you want to estimate the muscle forces in a mathematical way. So you've got some motion and you say, I want to estimate the muscle for the muscle activation that are generating the lowest kind of, they are minimizing the forces across the neck, or they are minimizing the square of activation. And that's, you can do that, but the problem is that if you do that, sometimes you get very on and off behavior of those muscles. So those muscles are activated when they are red, and not activated when they are blue. And as you can see here, just for a simple axial rotation of the head, you see this kind of, they are activated and non-activated, so a problem on and off behavior, which is not very realistic. It's not realistic because it's based on a mathematical function. So what we wanted to do, we want to use some experimental information, so the EMGs, to then estimate the muscle activation. So that's a bit kind of difficult to explain, I guess, in a few minutes. But what we did, we used some calibration trials. So we used some tackling and scrummaging trials to calibrate the model. So we get some head and neck motion, internal forces, and what we did, essentially, we compared the muscle activation estimated using a mathematical approach, so the static optimization, and we compared this kind of mathematical approach to a more EMG-assisted, is called, approach. And this kind of EMG-assisted approach essentially is using EMG to recreate muscle activation. And we did that just using the model as it was, model and plus the EMGs, but also or using the model EMGs and information from the MRI. And what we saw, that was an example of the simulation that we run. As you can see here, there is a run up towards the tackle. And if I stop it here, as you can see, there are activation, for example, on the left-hand side, as you would expect, because the head is moving this way. There isn't on and off behavior. There is a very realistic motion of the head as well. I can show you another time. As you can see, the muscle were activated at the beginning here, all red here, keeps red because the head is up, and then there's a higher activation towards the impact as well. So I just quickly want to show why that is quite important and what we found. So I'm going to show you here these graphs are not very big, but don't worry, I just wanted to show you the way that we kind of compare them. So here you can see different type of co-contraction indexes. So during the flexion, extension, and lateral bending, and the static optimization in the control contraction index is the blue one, and whilst the actual co-contraction index from experimental data is the black one, solid line here. As you can see, most of the time the static op is very close to zero. So the static optimization, so the mathematical approach, is not good enough to capture the co-activation of different muscles. Whilst the other two approach using EMGs and EMGs with MRI, which is even better, are really close to replicating the co-contraction index that you see during the actual experimental data. And you can also see, like, visually by the amount of red kind of lines that are moving from here to here. So, long story short, using this kind of EMG-assisted, in the meantime, here you can see a scrum kind of double simulation, but EMG-assisted approach in computer simulation is very good because you can, replicate accurate co-contraction, and you can estimate quite reliably the activation across different MTUs, you don't have this kind of on and off behavior. The problem is that it's very time consuming. You need to do an MRI, you need to, it's quite a long way to do that. And at the moment we have only a single participant with an MRI. All right, so finally we are towards the end of the presentation. So the last minutes, guys, so keep strong. We get to the end. And finally, I'm gonna introduce you to the a couple of simulations that we've been running here. So in this case, I'm showing you two different views of the same kind of head first impact during a tackle. In this case, there's a sagittal view and there's a more like a frontal view. And as you can see here, essentially what we did, we used muscle activation that we got from the previous study. So we started, we kind of hypothesized that the muscle activation were not changing across the simulation, and the simulation was run only for 50 milliseconds. And we applied the force that was generated, measured, using the dummy head as it was applied onto the head here. Just to give you a bit more information, we run a lot of simulation, and the reason why we run a lot of simulation is that because we wanted to essentially try to get all the different type of conditions that could happen during a tackle. So we did change 177 neck angles, so from -30 to so from 30 degrees of flexion to 30 degrees of extension, 0, -15 lateral bending both sides, and axial rotation both sides as well. We used two different type of loading with different magnitude and rate as well. And we used 7 different loading conditions to the head. So we simulated loading applied on the center line of the head from a anterior cranial, central cranial, and posterior cranial here, but also lateral and forelateral. So lateral, posterior, lateral, medial, posterior, lateral, medial, anterior, and lateral, anterior here. So if you do the calculation, that would be that kind of number of simulation. And that's something I already kind of started talking about before. So really, this is an example of how you can integrate experimental stuff with kind of computer simulation or theoretical kind of simulation. And that was the same, that's a kind of the same idea of the slides I showed at the beginning, where you got information coming from in vivo, information coming from in vitro. So in vivo EMGs and kinematics, in vitro the tackle force. Essentially, you run a simulation for 50 milliseconds, and then you'll run a forward dynamic simulation, and then you calculate what are the intervertebral joint loads, so the joint reaction forces between the vertebra in the model. So what's the take-home message? The first one, which I'm very happy to talk about with you guys later on, is about technique, essentially. And the first thing that we saw using the data that I'm going to show you later on is the neck flexion angle at the time of impact had the largest effect on neck internal loading. So it means that it doesn't really matter if you have got a quite high lateral bending or axial rotation kind of angle. Really, what was changing the internal loading was really the neck flexion angle. And there is a kind of quite easy explanation to it. And if you see this kind of position, if you see this kind of position of the head, if you look at the cranial posterior one, the force application, for example, you can see that this is not essentially going exactly through the whole spine here. But the more you flex your spine, what's happening to your spine is that your spine is losing this kind of curvature, and the spine is stiffening up a lot. And this is a very dangerous position you are putting your neck onto. And because the spine being very stiff, it means that the force is going through it very fully. So there's no way to dissipate energy using motion. And for example, this kind of cranial cranial posterior impact becomes very much in line with the line of the spine, for example. And that could happen for the other ones as well, a different type of flexion angle as well. So take home message one, neck flexion is bad, which, you know, is kind of in line with all the kind of box marked and rugby safe kind of guidelines. When, you know, you're a coach and you say, look up, I think that's quite important, not only to see what's happening in front of you, but also to avoid higher forces applied onto your neck. I mean, this is quite a busy slide. It's quite difficult to see what's happening to myself as well. But I want just to show you that, just to give you an idea of the data, you know, the kind of amount of data we had. But what I would like you to focus on is the change of color in the slide. So these are different loading for different vertebra level, a different type of loading point of application of the load. And as you can see, the color really is just changing in this direction all the time. Okay, these are more shear forces or compressive forces, and that means that with this kind of direction is the direction of the flexion extension. So it means that you know, the lateral bending and shear forces are not really playing a big role in sorry, the lateral bending and axial rotation are not playing a big role in this case. And I can show you potentially a bit easier kind of way to convey the same message is, you know, if you look at the same data but from just one side of the three-dimensional kind of cube, you can see that this flexion extension, the flexion extension is essentially changing a lot. The compressive load here, that's the maximal compressive load across different simulation, and that's neutral. Here is neutral, and here is flexion, and here is extension. So as you can see, the you know, the higher is the flexion angle, the higher is the compressive load, and that is true for different type of loading point of application as well. The big take-home message to me for today is that the actual injury mechanisms for us, I think there's a bit of a spoiler at the top of the slide, is buckling. So buckling is for us the actual injury mechanism during rugby injuries, and you can see that because, you know, here, for example, flexion, a hyperflexion, as an injury mechanism is mainly described when you apply a force very much at the back of your head, and what's generating is very high rotational force, a rotational moment, flexion moment, and all the vertebrae are flexing in the same way, in the same direction. With buckling, you got this kind of type of force, which is actually quite similar to the one we see here. And the type of motion of the vertebra is different across the different level of the spine. For example, you got a flexion of the lower cervical spine and extension of the upper cervical spine in the first or the buckling, for example. And that's an example of it. So this is, you know, a neutral cervical spine, and then you got flexion here and an extension, flexion in the lower part of the cervical spine, extension in the upper part of the cervical spine, which is something you can see as well here. I'm going to show you a bit better later on. But also in this simulation, we can see there's this kind of flexion here and extension of the upper part of the cervical spine. Really here, you know, we can talk about that later on. This is another type of the same kind of data. We got more like average value of a compressive anterior posterior and flexion moment with standard deviation as well at different level. What you can see here is that essentially nothing in what it seems. That was my kind of a way to do, you know, to describe it, because sometimes if you just a video analysis, you will see that the motion of the head looks like very much in hyperflexion because the head is going down and you see this kind of flexion. But in reality, what is happening to the spine internally is a buckling type of motion. So if you look in a video and you see that the head like going flexing, going down, doesn't mean that is an hyperflexion type of injury. And that's very, you know, that is very much visible here. And it's mainly for the cranial posterior and the cranial center, where if you look at the compression type of force is very high for very kind of high level of flexion, and it's very low for high level of extension. And that's essentially the same across the different type of point of application. We can talk about that later. The main thing I want to highlight is that the loading pattern here, with a high compressive force, with kind of anterior posterior shear forces, which are changing across the different type of level of the cervical spine, and mainly they are changing even if you go towards a more anterior point of application, are very much loading that are characterizing a buckling type of injury, and rather than hyperflexion. So we don't believe that hyperflexion is actually the mechanism, also because the flexion moment is not as high as expected. In fact, in these kind of graphs, I also added this kind of gray line, which is related to the highest kind of injury thresholds, or both for like compression, anterior shear forces and flexion moments. And what we want is to the main kind of messaging in terms of what's happening is that a buckling kind of injury was doing is moving the spine from a equilibrium point, which is before the impact, to another equilibrium point, which is when you accept the first part of the load. And to accept the first part of the load, the spine is essentially moving in that way with a different motion of the lower and the upper vertebra. And then you apply, then when you apply other load on top of it, then you might see, a more like a flexion type of injury. But the injury really has already happened, because the peak compressive and shear forces happen before reaching the high flexion angles. It's a question of, it's a matter of timing as well. So just to, kind of to give more like a applied type of messages, the importance of technique is very high. A good technique can save life to me, and that's much more important than muscle strength or activation. So of course you need to have a specific level of muscle strength, but the problem of muscle strength is that it can also increase the compressive load at the neck. So we can discuss that as well later on, I guess. This is just a hint for the future. So actually last week we've been running other simulation where we managed to recreate a first order buckling here, where you can see the vertebra moving differently. So extension, so flexion lower, extension upper. And here there is a ball carrier. So we're using a Contal model here as the one I was talking about before. We've got a sphere on the skull, and the torso, ball carrier's torso, is kind of model using this kind of plane. And we managed to recreate this kind of type, buckling injury. Not only the first order buckling, but also second order buckling, where you got even 3 different type of motion. You got flexion, extension, and again flexion here. So as you can see here, flexion the first C7, 6, and 5, and then you go 4, 3, 2, like extension, then flexion again. Conclusion, I'm a bit over time, I'm sorry about that. The first one is the importance of experimental data. I mean, even though I love computer simulation, I do realize that when you have good experimental data and you get experimental data from different sources, your simulation become more realistic, and that's a very important thing to do. So spend time in the lab, spend time like understanding what's the best way to design your in vitro and vivo study, because that will be fundamental to run then simulations. In terms of modeling, less is more. So as you can see, I've been mainly showing you models without lower limbs, for example. I don't need that. I need to focus on the neck, and I rather give more details related to the neck and the neck anatomy and muscle parameters than adding other bits. And the third one is in silico, the importance of this kind of in silico approaches to me. I mean, hopefully in the future we will see that stakeholders or governing bodies, as was happening in the past, will give quite a lot of importance to biomechanical studies, and in this case, computational studies that could be used to inform the design and potentially ensure this kind of translation to real world decision-making processes. You know, for example, we can talk about the tackle height, you know, rule as well, and how has been trialed in the UK as well, if you want. But that's everything for me. Oops. And so thanks a lot for listening to me and tuning in.
Dario, thank you very much. That was absolutely superb and very eloquent. I know we've got some questions that have come in, and Jerome's got some very practical questions as a field side clinician himself. Yeah. I want to start off by just asking you about this sort of research. We've got 300 people here listening to you, and I'm sure wondering if they want to try and do research of this sort of intricacy and this sort of standard. How do you conceive it? How do you go about modeling the research, and how do you go about funding it? Because this is obviously not cheap research. Can you talk us through that process if you went through?
Yeah, I mean, to be honest, I think I've been quite lucky because I came over here from Italy 9 years ago now, and in terms of funding, I'll reply about funding first. It's a very difficult research to get funded, and when I came over here, I was working on a project funded by the World of Rugby, which was IRB in the past. And we were working on a rugby Scrum project that then led to changes in the rules of the Scrum, and there was a worldwide. So that was a very big type of project. So to me, it was a quite easy transition from to do some. That was mainly kind of experimental study related, but essentially people started to know what we were doing in our kind of research after that, and then I managed to get some funding from the. From a charity, which is the RFU Injury Prayer Foundation, but also tried to be honest, tried to get some funding from other research councils in the UK. And unfortunately, when you're talking about sport, it's difficult to get high level of funding as you're talking about more clinical type of stuff. So I think you need to be clever and try to merge what is related to sport medicine and injury prevention to more like engineering or clinical stuff if you want. So for example, you can apply the same methods to work on spinal implants, for example, and of course the type of loading and type of motion are different, but the same, you can apply the same methods, for example. And in terms of how you do you approach that, I think you need to have potentially a couple of people or 2-3 people working, collaborating with you, and you need to have expertise in modeling, expertise in experimental tests as well. So for example, it took like 6 years to me to do well. So I've been presenting work from 6 years ago, and everything started with myself in the lab, and then little by little I started to create models. So it takes time. But I think as you can see now, I mean, the other thing is that now, is everything is open source. So all my models are open source as well, and I'm very happy to share them and my data is open source as well. So I think now we got to me the exciting bit is to being able to share the data we have and share the model that we have, so that we can make that kind of research happen more quickly, rather than starting from scratch. It doesn't, to me, it doesn't make sense if someone now in South Africa would start doing a model from scratch rather than starting from my model, or another guy model. It doesn't matter if it's mine or not. But I think sharing is important, and I think that's my view on it.
Brilliant. That makes great sense. Jerome?
Thanks very much, John. Thanks, Dario. Thanks for the presentation. Really good. Just a question around maybe some application as well. I wanted to, I was interested in you speaking about that maybe World Rugby or the IRB basically, had used the models to kind of change perhaps scrumming or influence the rules around scrumming. What I wanted to know is that, when you look at your modeling further, where do you want it to go in the future? Which areas do you actually want it to start influencing? Which areas in the game, or which parts of, or which rules would you like to see this influencing?
I think, I mean, tackling now is, if you talk to people, tackling is the focus all the time. There are other things that you can try to focus on. For example, there was the leaning on during the scrum. So when the people were like leaning against each other before the actual engagement. And there was another thing that I think was quite interesting to check. But I think they also banned that kind of thing before, when they realized that the forces before the impact were too high. But yeah, so to answer your question, tackle height to me is the future. And as you know, I guess they trialed in the UK different tackle height rules. So in the championship, they asked to lower the tackle height, and they trialed that. And the problem they saw that most of the tackler essentially, since they couldn't, so the ball carrier, because the tackler couldn't tackle them very, very high, they started to crouch as well. So the actual, for example, percentage of concussion at some point increased as well. And to me, that was my comment on it is that they mainly focus a trial that with respect to concussion, which is very important, and is I think that's something that you should do. But for example, whilst you do that, also if you lower the tackle height, what you are doing, you are essentially putting this kind of player, the tackler, in more, they're going to be more likely to get a cervical spine injury because they're going to be more flexed in terms of the head flexion. So what I want to do, potentially the last simulation I show, maybe I can show that again. This one, that this kind of approach when you have a sphere here and you simulate the ball carrier torso here can be even improved, and you can really get information, for example, from video analysis, or you can do some better kind of stage tackles in the lab and try to highlight what are the most injurious or the most dangerous type of situations. And maybe, for example, to me, in a question that I might ask you is like, is there, it's possible to highlight what are the most dangerous type of tackling in terms of angle, or the tackling in terms of playing situation. So there are so many variables that could be included in that simulation. So at the moment I'm just simulating some a head going through a torso, but that could happen in many different ways, and it could happen at different times during the game. So how do we include that into my simulation? How do we include, for example, the psychology of that player into my simulation? So if you're fearless, or you are more prone to to try more like dangerous tackle. So I think that's something that could be, that's some we can look at. And maybe, I know in South Africa, you guys, you got very good rugby science researchers. So, and you're doing lots of more kind of psychological and video analysis or epidemiological research that could be very important to inform my simulation. So yeah, so I think tackle height to me will be the next one, but I'm very open to other suggestions if you guys have.
Okay, great. Just adding on that, I want to pick up on that and just ask you, I mean, again, is there a bit of a crossover as well with regards to overseas sports like NFL? Are you finding that maybe there are similar models there, and is your work influencing that work that's being done as well? Great
question. Yeah, so yes, there are. Unfortunately, there's not much in the NFL, and what I believe, the technique is completely different. So you don't see like rugby players like going against each other like rockets. So rugby players to me have got better technique than NFL in tackling, at least, than NFL, and there are different type of forces and an acceleration experience during NFL tackle than a rugby tackle. But yeah, so there are a couple of researchers doing that, and I'm very happy to share the names as well. And I think there is something that we can you know, we can work together as well. Yeah, I think NFL as a game itself and as a governing bodies related to that is a bit less open than the world of rugby or rugby in general. So it's more difficult to dive into the kind of you know, changing rules or, you know, the government related type of guidelines.
Yeah. Thanks. Just a question from Loisa Macrina, if I can put it in the words that actually Loisa has said it there. He says, in terms of the impact used in your punching bags, is the speed of acceleration and point of contact standardized?
Yeah, so good question. So it wasn't, in the sense that we used, like, our technician was pulling the rope attached to the bag. In our statistical analysis, we considered the bag velocity as a covariate. So the data are you know, already kind of, you know, that kind of speed is considered in the data. So we couldn't standardize it, but you could use, I think, you guys, Sharif, I think, and Nick Berger, they used a pneumatic type of activator to accelerate the punch bag. It's always at the same speed, and that would be, you know, that would be a better thing to do. We didn't have it, so we just used a technician to do so. But yeah, but the speed actually wasn't that different at the end of the day. So it was I think between 3 meters second and 4 meters second.
Okay. Would you also have recorded the speed of the subject as well? Was that accounted for as well? Yeah.
We recorded everything, yes.
And then his other question was around if you have maybe just real world application. He was just asking if you used norms basically from any sport or from any pro sport.
If I used what? Sorry, norms?
If you used any norms from sport to actually compare with your models.
Well, what we did, we compared, what you can do, you compare the forces that you get out from other kind of cadaveric studies. Cadaveric studies and in vitro studies are mainly related to automotive or, you know, kind of accidents during car accidents, for example. And they are replicating that. Usually you got your specimen, the specimen is accelerating against the ground or something. So there's not much from other sports, unfortunately. So that's the problem in relation to sport medicine. You know, if I want to really compare the joint reaction forces at a specific vertebral level during a rugby tackle or, I don't know, hockey kind of injury or you know, a ride kind of accident, is difficult to do it because there's anything about those sports, or there's very little in terms of that specific force. Whilst I can get it from in vitro or in silico study done like in more controlled situations, or like car accident or stuff like that.
If I may ask a question from Brad Galbart. He asks, so where do you think the failure most commonly occurs, at the ligament or bone interface? The
failure, well, very good question. So I should say, I don't know. So the most common injury is the bilateral facet dislocation. So it's more that kind of facet joint. I think it's a combination of the two. I think the ligament will probably go first, and then you got a bone. But you know, the bilateral facet dislocation is more the kind of translation of the vertebra. There's not much bone. It's not like a burst kind of injury, but the bone is kind of there's the fracture really. It's this kind of sliding of the bones. So it's more, I think the side would be more ligaments.
Okay. Tell me, just with the model that you also pointed to, where you spoke about neck flexion having the largest effect on internal loading, and also just describing your buckling model basically for injury, in terms of injury. I wanted to just understand the practical implications of that on maybe what we are doing from a injury prevention perspective, and perhaps even from a rehabilitation perspective. Are you finding that there has been some use of this work in that line?
I think what I believe from our kind of data, what is important to show is that being buckling towards the most important mechanism, and flexion extension the more related to the injury. I think technique, coaching technique and is the most important. Coaching the right type of technique is the most important thing to do in terms of prehab. And of course, you want to be sure that you got muscle strength which is high enough, for example, to resist some shear forces. So there are some anterior, posterior, and medial lateral shear forces. You've got very kind of a high muscle strength for sure that you can resist a bit that motion, but there's nothing you can do for the compressive kind of forces, because if you got very high, very strong muscles, then even though if the force is coming from the top and you're compressing the spine, a very strong muscle is not doing much, because it's even increasing if you are compressing that kind of stiffening the spine a bit even more. So I would say that the first kind of application will be related to coaching. In terms of prehab, rehab, I think is to be sure that you have a very good muscle strength, but not an excessive one, because that is not you don't need to have a neck like that to so that you don't get injured. That doesn't work like that, unfortunately.
Okay. Just another question, sorry, from Jaden Mays. He asked, from this research, does this raise the question of whether the development of protective gear is warranted?
Well, we haven't done it, so we haven't added any kind of protective gear onto our kind of models. In rugby, I think, again, protective gears are not very much used, and I believe that in this case, a protective gear is not changing much. If you got a rugby hat or stuff like that, it's not gonna. It can help if you got if it happens to you, you're gonna get like a very sudden kind of hit, and you can avoid, for example, a skull fracture, but that's very unlikely. So if you want to really minimize injuries, it's more the technique rather than having any garments, to me. And that's also shown if you look at the NFL, for example. They've got all the protective garments. They are less technical in the kind of tackling technique, and the type of injuries are much more severe as well. So long story short, I think I wouldn't see research on protective garments as a priority, unless people come up with like a very kind of smart clothing or tissue that will increase the type of will improve the resistance of the neck motion in a specific way. But we're talking about the future here. But that case, if you got something that with your muscle activation is stiffening the neck in the right position, that would be good.
Okay.
Great. Thank you very much, Jerome, for fielding those excellent questions. And Dario, again, thank you for a wonderful, wonderful presentation. Congratulations on some superb work. I think it's a type of work that really is going to influence the game and decrease injury rates. It affects not only clinicians, but coaches as well. And I think that's a point that you've made, is that this is something that can be applied in a very practical way, and in so doing make a game that so many people are fond of that much safer. And we appreciate you for sharing your time this evening with us, and really such a high-level presentation is a real treat when we get to witness research like that. So we certainly hope we can collaborate one day with South African researchers. And
yeah, I hope so. I mean, we know each other, so guys, just drop an email.
So we must keep doing what's good for the game, and please stay involved with the game, and hopefully we can host you for an update one day. But thank you very much for your time. For those who would like to see the presentation and the other WiSH presentations we've hosted, it will be on the WiSH website in the coming days. For those of you looking for your CPD points, please stay on. At the end, you'll see the link that you have to connect to for the survey, and you'll be guided through the process to obtain your CPD points. Our administrator, Nadine Peterson, has worked very, very hard this week to make sure that she gets those certificates out, and hopefully we'll be up to date with those CPD certificates at the end of the end of the week. We're just putting up here the next talk, which you'll see next Tuesday. Again, we're very privileged to host two excellent speakers who will be talking about the long-term effects of concussion in sport, chronic traumatic encephalopathy, and we'll have another speaker, a South African speaker, talking about motor neuron disease in collision sports. So please join us next Tuesday at the same time for that. Again, a big thank you to all of you for participating, to our sponsors, Acino and Lita Pharmaceutical Company, for your support. Dario, a last goodbye, and thank you very much once again. All of you have a look at that QR code and the link. Have a look at the social media links to follow us on Twitter and on Facebook. And please do join us for the coming talks that we have in the coming weeks and months. We look forward to hosting you again. A very good evening to all of you. Thanks.